So what happened? Well, the father, right? When he went to go make his cells, he had an X and a Y. He duplicated his X, he duplicated his Y. But one of the Y chromosomes that had the plus SRY gene, it got transferred. It got switched. Did you hear me? So ready? I'll draw. There's the X that he got from his mother. There's the Y that he got from his father. Okay? The SRY gene is at the tippity top. And so when they go to duplicate, and they crisscross, then I'm left with a pink with a little bit of blue. See that little bit of blue? That little bit of blue represents the SRY gene. And then here, little blue with the pink, oh, that means a minus SRY now. See that? So that little bit of pink right there, because that blue is missing, that's the SRY gene. It's been transferred onto the X chromosome. You got me? See that? So when I go to do meiosis 2, I'm going to have 4 cells, and I'm going to have maternal chromosome, maternal with what was the SRY. So an X chromosome that's unadulterated, an X chromosome that's carrying the SRY gene. Did you hear me? And then what? Oh, the Y chromosome without the SRY gene, and then a Y chromosome with the SRY gene. You see that, guys? Those are 4 sperm. I'm talking about males, the 4 sperm. If this sperm fertilizes the egg, then we got a female that's got SRY gene positive. You see that? That's a true hermaphrodite, isn't it? Remember I told you, XX plus the SRY, that's a true hermaphrodite. Yeah? Unambiguous genitalia. Okay? No real internal reproductive structures. And looking like and being genetically female. But just kind of all confused. You got me? So here we're talking about these non-disjunctional events. And you can see now that Turner syndrome, right? I'll draw you one to exemplify Turner syndrome in this case. In this case, it's the whole chromosome that's missing. It's not a section of chromosome, it's the whole chromosome. Right? In this case, it's not so much the non-disjunctional event, it's what? It's the crossing over event, right? So the crossing over event can give rise to diseases, right? If we're talking about the SRY gene on the X chromosome, right? Then the crossing over event could take that SRY gene off the telomeric end of the Y chromosome and put it on the X chromosome of the father, of one of the father's genes that are destined to one of the sperm. If this one fertilizes an egg, then it's going to be female. If this one fertilizes an egg, it's going to be male. You got me? And normal. If this one fertilizes that egg, then it's going to be a true hermaphrodite. If this one fertilizes the egg, it's going to be a pseudo-hermaphrodite. You got me, guys? Did you see that?
But most of them can't reproduce.
When these meet up with that egg,
right,
that's normal, then yeah, both of them are going to have problems because neither one of these can reproduce.
Gotcha.
Hermaphrodites can't reproduce, whether they're true or pseudo-hermaphrodites. They cannot reproduce.
Do you think like every man that is able to make sperm, do you think they've created that at least once?
Yes, absolutely. Yes. Absolutely. So being a hermaphrodite is nothing more than a roll of the dice, baby. That's what you get when you play the game. You got me? So you got to be aware of that. Someone comes in and says, hey, look, if your kid's normal, who cares? So what if you can't reproduce? I mean, granted, it may be a blow to their psyche, but they can still have fun, put a smile on their face, and succeed. They're alive. That counts for something. At least they're not retarded. Right? Trisomy 21. Oh, there's another one, guys. Klinefelters. Klinefelters, these are examples of non-disjunctional events that can occur in the sex chromosomes. Klinefelters is what? Now you tell me what happened. Was it a mother's egg who didn't separate the two X's that it needed to when it needed to? Or was it the dad's sperm who didn't separate the X and the Y when it needed to? Oh, could be either one. You get me? Do you see? So is it, you start pointing the blame at each other. Not much you can do. Now there's this other one called XXX. That's a superwoman. For the most part, nothing wrong with you. So some of you may actually be superwomen, not even know it. Okay?
What happens if you are? Is there anything? You could be perfectly normal.
Like
and
physically,
have
is there a sign?
Yeah.
No, there's no. The fact that you have extra genetic material, the X inactivation, I don't even know if there's a clinical syndrome. There may be like a small amount of mental retardation. So those who like aren't so smart in the population that are females, some of them, not all of them, because that's not true. So some people who are on the lower end of intelligence scale, who are female, could in fact be superwomen. Could be XXX, but not all of them. Because it's not really true. So yeah, I think it depends on which X chromosomes they inactivate and what other genetic material. Because what did I tell you? Females are complicated. When you finally got it all together, and okay, I'm female, I got my X, I'm a female zygote, I'm gonna become a female because I got everything that's, genetically what's gonna allow me to become physically female. Even during that, all those cells, one of the two X's has to be inactivated. Not completely, but sure enough, X inactivation is part of the normal female genetic design. You got the two X's, good. You only need one. Figure out which one you want to shut down. Got me? Not completely, but for the most part. Now, and we talk about males, just in general, because males are XY, if there's something wrong with the X that I inherit, there's a disease. So when the X is fragile, it's called Fragile X syndrome, and it is the most common form of mental retardation in males, guys. You understand that? So you come across a mentally retarded kid who doesn't look like he's got Down syndrome, more than likely, it's a boy, it's Fragile X syndrome. His X was fragile. He only had one X. You start messing around with his X, what the hell is he going to do? Mental retardation. Guys, that's huge. That if there's something wrong with your X chromosome, you're guaranteed to have mental retardation. That sucks.
Question.
I'll get your question.
You were mentioning that Turner's is like a form of mental retardation.
There's mental retardation associated with short stature and a webbed neck. Yes.
Like do those people live like a long?
No.
No, they don't.
No. They have issues, but they can live up to 40, age 40. Yeah. So
I have an aunt. She's mentally retarded.
Yeah.
And she has like a few other things.
Does she have that? Is she short with the web neck? You don't never notice? No. Sometimes they don't have the web neck.
No, like physically speaking,
Yeah.
she's fine.
She's fine. And she's been mentally retarded her whole life.
Yeah, like they diagnosed her. She has like the mentality of like a 3-year-old.
Yes. And how old is she?
She is about 50.
Well, 50. Yeah.
But now she's like.
But she interacts. And she can move, but she can move and she can do stuff and she can talk and respond. No.
Like now she always feels like she's falling. Like they always have to have her seated.
Oh, that's man. It'd be nice for them to test her to see what's going on there, because there's, and this is the thing. A lot of times, we don't get tested, and the doctors don't care. They're like, But you know what? It'd be good to know. Like it'd be good to know. Like if I'm going to marry somebody, we're going to have kids. I don't want my kids to come out retarded. Like you carrying that retarded gene. Right? Or am I carrying the retarded gene?
We can test that. Like they can test that.
I'm just
joking.
Just joking. But remember now, if I'm carrying the retarded gene and then my partner's carrying the retarded gene and then we have kids because we never got tested, And if we would have gotten tested at least to see how close we were in consanguinity. Because I could be, you know what happens. You go to Europe, and next thing you know, you fall in love with somebody, you find out they're your first cousin. You just didn't know him. Or second cousin. Or third cousin. There's still consanguinity there. Did you hear me, guys? There's still consanguinity. And what does consanguinity mean? Consanguinity means, so consanguineous means you got similar blood types. Consanguinity means you got similar blood types, you got similar genes. Well, if my genes are similar to the genes of my partner and we have kids, then our kids' genes are going to be really way too similar. You got that? And if they're way too similar and I've got a gene that's bad or an allele of that gene that's bad, and she's got the allele of that gene that's bad because we're so much alike, then our kids are going to definitely have an autosomal recessive disease. You guys, you got me? So, Mendelian genetics. In a nutshell. Mendelian genetics. So you have autosomes. So either there's an autosomal dominant disease or condition, or autosomal dominant versus autosomal recessive. Well, here's the thing. The deal is you got a gene and you got two alleles. Okay? And either you have or you don't have a problem. Got me? So now, if we're talking about an autosomal dominant disease, then all it takes of the two alleles that we get for one gene, so one gene, two alleles. Everybody got that? One gene, two alleles. Two alleles, one gene. You got me? For most genes. This is where this shit gets difficult. Mendel couldn't account for some of these other stuff that I was talking about. There are other systems where we have multiple genes that are involved in the production and sustaining of a protein. More than one gene. So that means more than one set of alleles. You got me? In some cases we have one gene but with multiple alleles to it as well. So shit gets complicated. Mendel couldn't count this. So in Mendelian genetics, you're talking about one gene, two alleles in that gene. In an autosomal dominant fashion, all you need is one bad allele of that gene, you get the disease. Did you hear me? One bad allele. So, one bad, one of two bad. You got me? One of two bad alleles. Okay? Can I erase this, guys? Everybody good with that? It's definitely on the. And then I'll write this over. I'll write it over here. More towards it. All right. All right, so just to mention, so I see more students came in, we're going to, the students decided, all right, as a class, that we were going to give the test on Tuesday. Tuesday's this week coming up. So that way, you guys have a week to go over that test and the answers to that test and prepare yourself for the final, which will be the following Tuesday, okay? So the test will be Tuesday, not Thursday. Thursday, I will not be here. I mean, I'll be here because I have class, 2085 class. I will have office hours, right? But I won't be here for class at our normal time, 9:50, okay? If you want to see me, you can come see me. If you want to know your grade, come see me during my office hours, all right? I'll be here for the 2085 class. Yes?
So does that mean that the homework is due?
No. I can't reset the homework, so the homework will still be due that Thursday. Yeah. So you still have time to finish the homework, right? You'll have time to take the test and review the test and start next Tuesday. So test next Tuesday. Everybody hear me? Text next Tuesday.
Will we get the answers to that test?
Yes. Yeah, you will. That same day. Or sometime during the day. When I get back home, I'll email it to everybody because I have you guys on email list. All right. So what we were saying here, guys, so in Mendelian genetics, right? So and I'm spelling Mendel wrong, am I not? Is it two D's or two N's or something like that?
No, I think it's 2 L's.
Two L's?
I don't know.
One L, two N's?
One N.
One N.
It's fine,
Okay.
yeah, one N.
Okay, so, alright, so Mendelian genetics. So in Mendelian genetics, guys, you have, again, autosomal versus sex-linked. An autosomal dominant versus recessive. And sex-linked dominant versus recessive. And again, the same thing accounts. For you to get a disease in an autosomal dominant fashion, all you need is one of two bad alleles in one gene, and you'll result in positive disease state. Symptoms, whatever. Signs and symptoms, whatever. You got me? Now, in recessive, you need both of the alleles to be bad. So in recessive, you need two of two bad alleles in one gene to result in a positive disease state. Everybody understand that? Now, in sex-linked dominant, guess what? Same thing. You only need one gene to be bad. One allele of the gene to be bad. It winds up being that we're talking about, is it on the X or is it on the Y? Okay? Well, sure enough, the Y doesn't have much on it. The Y is the smallest chromosome that we know. It looks like this compared to all the others. And it's just the top, the little top of it, that the SRY gene is present. So when you're looking at X-linked recessive, or dominant versus recessive disorders, the idea still stands. Here you got one of two bad alleles per one gene versus two of two bad alleles in one gene. But now again, that depends, doesn't it? Because if I'm talking about a male, then what? I only have one chromosome. Do you agree? One X chromosome. Do you agree? And that X chromosome, most definitely I got from mom, because I got the Y from dad. Do you agree? Now, if that X chromosome has the allele on it, and it's bad, am I going to get the disease? I am, huh? Everybody see that? But now, so what really determines sex-linked dominant versus recessive, you can't look at the son. When you look at the son, you got to then go back and you got to look at the mother versus the daughter to the father. See that, guys? That's the link. The mother, why? Well, because the mother, what? Is XX. And the son, well, he's XY, but guaranteed, he got one of those X's from mom. Mom got one of her X's from dad, one of her X's from mom, right? Her son is going to get one of those too. Do you agree? Do you agree? So she may not, it may be an autosomal recessive disease where both our X's have little n, right? And he's guaranteed to get the disease. You see that? Because either one of the two that he inherits, whether he gets the pink one from his mother, because she got that one from her mother, or she gives him the one she got from father, he's going to get the disease. See that? But now watch. If it's truly, again, if she's got this, big and little n, whatever the disease it is, then she doesn't have the disease, does she? She's a carrier. But you see what happens? If she gives her son the maternal chromosome she got from her mother, then the kid's normal. The boy's normal. See that? But then what happens? If she gives this one to the son, then he's going to get the disease. Do you see that, guys? So what winds up happening? Well, when you look at, so this is a condition. This would be an autosomal. This would be a heterozygote, right? And if she's a heterozygote, and that gene, that allele of the gene, is the one that would cause the disease, the only way that she's going to pass that disease on is through her son, not through her children. Why not through her children, guys? Or less likely through her children? Because when you take that mother that has the X and you cross it with a father who's normal, so there's a 50-50 chance. You see the girls? The girls will be carriers or normal, but the boys will be affected. So what you have to keep doing is you got to keep looking. If she has any daughters, you got to look at the sons of her daughters. So this is where, guys, you'll see the recessive disorder being, the sex-linked recessive disorder being distributed throughout.
And she has carrier females. So yeah.
She would. She'd have carrier females, so her females will pass the trait on, or possibly pass the trait on to the son. So you got to, if she never has any daughters, then you would never know. So again, this is why you look at the children, and you look at the children's children, you go through pedigrees. That's why we use pedigrees, because the pedigrees will show. So how would I show a female? So here's mom. Mom's a carrier. Dad is normal. Everybody see that? They had 2 kids. The one kid is a carrier. The female's a carrier. She got married, and she had, 3 kids. And of those 3 kids, one of the females is a carrier, one boy is normal, and the other boy is affected. And you see how it skips a generation and affects only boys? And the females must be heterozygotes, and therefore it must be a recessive condition, a sex-linked recessive condition that only will occur when you got the boys, because they only get one X chromosome, and they're always going to get that X chromosome from mom versus the Y from dad. You guys got me? You understand me? Now it's true too that if the mother has a sex-linked dominant condition, then if she's only got one gene, she only needs one gene to have the disease, but she'll be affected. So when you go to look, you see, oh, the mother's affected or the father's affected. Then you'll see it's different. It's different. So the idea here is just to understand, you got autosomal dominant, autosomal recessive, you got sex-linked dominant, sex-linked recessive. That's typical what Mendelian genetics is. But remember I told you not everything is Mendelian genetics. So separately you have dominant traits, right? You have codominance, incomplete dominance, and then we talked about penetrance and expressivity, right? So those are what we call out of the norm. These are outside the norm of normal Mendelian genetics. This is the inheritance of man. Because it's not just about what Mendel found. There's other stuff that's a lot more complicated. Okay? And so that's what gives rise to codominant traits in systems, incomplete dominance traits in systems, versus complete dominance. Okay? And then, of course, you got to deal with expressivity, and then polygenic inheritance, and polygenic gene disorders, and then, of course, polygenic gene disorders, and then take into account environment, and that the environment can always have this impact everywhere and anywhere along that beginning to the end of how the cell does what it does. Okay? Any questions? Any questions at all? Yes.
Fragile X is also non-disjunctional, or?
So no. So fragile X is just something's up with the X chromosome. We don't know what it is, but sure enough, because it's fragile and because they're XY, then once that X is fragile, you don't get one X, you're gonna get severe mental retardation. And this again in boys, not so much in girls, because again in girls. You're already trying to figure out which one of the two am I going to inactivate. So if it winds up being that you inactivate the one that's fragile, then you're good to go. It doesn't matter. It doesn't hurt you. And that's where you don't see females who have fragile X. You don't see the same severity of mental retardation. So, and that would make sense because they have two X's. Boys only have one. If you mess with the one I have, and I have no other, that's why I get severe mental retardation in boys. So let me write that down.
This was in the video.
M-R-E